Good morning, dear students. We are continuing with module 5 and today we are going to cover the topics like design of counter that counts a particular sequence. Now, this is the first problem that we are going to see. Design of a synchronous counter that counts 0, 3, 5, 6, 0 and so on using T flip-flops. So, in any counter design, the first step will be to determine the number of flip-flops required. So here we can see that the counter is having only 4 stable states 0, 3, 5 and 6. So what is the biggest count? It is actually 6. 110. So how many flip-flops it requires? 3 flip-flops. Now using 3 flip-flops, you just evaluate what is the maximum number of states possible. It is 2 raised to 3 or you can call it 8 states. But here we need only 4 states for the sequence. So the remaining 4 states will remain as invalid states. And for K maps, we put don't cares for the invalid states. So the invalid states are actually 1. We can say it as 2. Then 3 is already there. Now 4. 4 is invalid. 5, 6, 7. 7 is also invalid. So these particular states are, these are the invalid states and these are the valid states. Now we can draw the state transition diagram this way. This is 0. This is 3, 5, 6, 0. It's counting this way. Now, what is the next step? The step 3 is selecting the type of flip-flop. Here, I have already told in the question to choose T flip-flop. So, you should know the excitation table of T flip-flop. What I said, like you should know the QN plus 1 combination. You know it's always 0, 0, 0, 1, 1, 0 and 1, 1. You should know to write this. Now how will you read this? When your QN plus 1 is 0, 1. Your T is 1. You have to know this way, by heart this table. So the next step is preparing the counter's excitation table. For counter's excitation table, you require present states, then what you need, next state, and then what you need, required excitations. So you have 3 flip-flops. The present state constitute Q3, Q2, Q1. Next state also has Q3, Q2, Q1 and T flip-flop has only one input. So your input of third flip-flop is T3, second flip-flop is T2 and first flip-flop is T1. Now, how will you form this table? First, the step is to write the present state. What are your present states? Your 4 valid states. You have 0, 3, 5, 6. These are the 4 valid states. You write them in the present state. Now, using this present state, you need to construct the next state. For example, first case, your present state is 0, 0, 0. What is your next state? From 0, it should go to 3. So, your next state will be 0, 1, 1. Now, take the next present state, 0, 1, 1. If your counter is in state 0, 1, 1 or it is counting 3, what should it count next? It should count 5, 1, 0, 1. If your present count is 5, it should count next 6. If your present count is 6, it should next go to reset state because it should start counting again. Now I hope constructing the next state is okay for you. Now we'll go to the required excitation. Using Q3 in present state and Q3 in next state. So it actually forms QN and QN plus 1 of the third flip-flop. Q3 and Q3 of present state and next state. You should find T3. For example, here Q3 is 0, here Q3 is again 0. For 0, 0 combination of Qn plus 1, you have T3, 0. Likewise, you should take Q2 and Q2 of present and next state to construct T2. Similarly, T1 using Q1 of present state, Q1 of next state. So, you should complete this table. Next is obtaining the minimal expressions using Q3, Q2, Q1 in the present state. You're going to form the equation for T3, T2 and T1. Look here, using this Q3, Q2, Q1, you're going to construct the K-map for T3 separately, T2 separately and T1 separately. So T2 you don't need to find, because even if you form the K-map all are ones, and for the invalids you put don't cares. So definitely T2 is going to be 1. So you need to form the K-maps for only T3 and T1. So please don't forget that for the invalid states 1, 2, 4, 7, please put don't cares. Okay, put don't cares. Then you group. Here you can form here it's a quad is being formed. Here also quad is being formed. You can read that. You'll get T3 as Q2 and T1 as Q2 complement. T2 I already said it is 1. There's no need to form the K-map. Now you draw the final circuit. So this is how you're going to design a counter if a particular sequence is provided. A particular sequence. Okay. I hope this problem number 1 is clear for you now. Let's go to the second problem. Second problem. So here we are going to design a synchronous counter that counts 0, 1, 2, 4, etc. Again 0, 1, 2, 4, 4. Okay? It's not etc. 0, 1, 2, 4, again 0, 1, 2, 4 and so on. And it's specifically told. So you should always listen to the question. Okay? Here it is specifically told that the unused states must go to 0 on the next clock pulse. So if you are given with a question like this, what you should do? So again start. What is the first step? You should decide the number of flip-flops. The biggest count is 4. It can be represented by 1, 0, 0. So it requires 3 bits. Sorry, it is wrong here. It's actually 3 bits. It requires actually 3 bits. Okay. It's not 4-bit, 3-bit. It was a mistake. I'll correct it in the PPT and give. Don't worry. Now, what are the invalid states? 3, 5, 6 and 7. So they are usually represented by don't cares in the map. That is what we usually do, right? If a counter design is having some invalid states. Invalid state means using 3 flip-flops you can actually have 2 raised to 3 8 states. But you are utilizing only 4 states here. The remaining 4 states you usually consider it as invalid state. And you usually represent it by don't cares in the K-map. But here, what is the difference? In the question itself, it has been told that the unused states must go to 0. So, in the design itself, for these invalid states, you are going to specify the next state. You don't need to put don't cares. I'll show you why in the next slide here. If it is specifically told in the question like this, it's not the don't cares that you have to put. You have to make the design in that way. So this is the state transition diagram. The real states are 0, 1, 2, 4. but all the other invalid states 3, 5, 6, 7 should go to 0. This is what the problem requires. Now I'm going to use D flip-flops here, so you should be very thorough with the D flip-flop excitation table. Now we are going to construct the counters excitation table. So look here, we need, what all we need? Present state, next state and required excitations. So present state, you write all the states. Okay? But consider them separately. See the valid states here, 0, 1, 2, 4. Okay? So this is a valid state, 0. This is a valid state, 1. Then which one? 2. This is a valid state and 4. This is a valid state. So for all that, please write the next state first. So if it is in 0 state, look here. If it is in 0, 0, 0 state, what should be the next one? It should go to count 1. Because my sequence is like this, 0 should go to 1. If it is in 1, what is the next state? It should go to 2 because my sequence is like this. If it is in 2, it should go to 4. Now from 4, it should go to 0. So these 4 valid states you write first. In order to make it clear for you, you first write the next states of your sequence. Then you go to the design of the other things. Now these are the invalid states. This is my first invalid state. This is my second invalid state. This is my third invalid state. And this is my fourth invalid state. Okay? Now what I should do? Take the first invalid state, 0, 1, 1. Is it there in the sequence? No. So what is required in my design? It's being told that if that count is not there in my sequence, it should go to 0, 0, 0. So you put the next state as 0, 0, 0. That means that if the counter accidentally enters count 3, it should reset soon. Next state, 0, 1, 0, 1. Look here, 1, 0, 1. It's not there in my sequence. So my designer has told that it should go to reset state soon. The same with this too. It's going to reset states as well. Now my present state and next state has been finished. I can form the required excitations. Using Q3 and Q3 in present state and next state, I'll find D3. Similarly, using Q2 in present state and Q2 in next state, I'll find D2. Now, using Q1 in present state and Q1 in next state, I'll find D1. This is how I'm going to fill my required excitations. Now, I'll obtain the minimal expressions. Here, I have not formed any of the K-maps. Why? Because you see this. You always observe your excitation table and then only go for K-maps. Don't just suddenly go to K-maps without observing what you actually got in the required excitations. So what do you actually form for K-maps? Using Q3, Q2, Q1, you will form the K-map for D3. Using Q3, Q2, Q1, you will form the K-map for D2. Using Q3, Q2, Q1 again, you form the K-map for D1. But look here, I'm taking these as my inputs, Q3, Q2, Q1, but this is my output. Look here. If I need to form an SOP expression, only one term is 1, all the others are 0. Here also, only one term is 1, all the others are 0. For day 1 also, only 1 is 1. So how can you read? You can read this directly. Look here, this one, what is the corresponding here? Q3 complement, Q2, Q1. This is what is written here, Q3 complement, Q2, Q1. Similarly, for this one, D2, look here, Q3 complement, Q2 complement, Q1. Look here, that is what is written here. Now the next one also I can write. So there's no need to form the K-maps here. You can write the equations directly because only one is present and all the rest are zeros. Now I can draw the final circuit. I hope by now you know how to draw the final circuit. Now that's all for today's class, specifically the design of counters that goes through a particular sequence. Thank you.